Hi folks, welcome to 3.2 part 4. And in this video, we're going to talk about the standard form of the quadratic function. Okay, this might be one that's familiar to us. So unlike the factored form, which is sort of like two sets of parentheses, and the vertex form, which was like one parentheses, there are no parentheses here. And instead, we have these numbers, A, B, and C, next to our x squared, x, and our constant, okay? Now, the standard form of the quadratic function is, like the other two forms, useful for some things and less useful for others. And so I would say that the one thing that the standard form is really useful for is in finding the vertex, okay? It's not as easy as vertex form, but it's easier than the factored form, okay? And I would say least useful for finding our x-intercepts. And sort of like the vertex form, it's not as bad, but it's a little bit more work than the factored form. Okay, so I would say the standard form is almost like if you think about the Goldilocks and the Three Little Bears, it's sort of the one it's not really just right, but it's not too hard here, or it's not too easy here, and it's not too hard here. So it's kind of like a nice middle ground, okay? All right, so let's do two examples, okay? So I will warn you that the numbers are a little bit less nice in examples 5 and 6, okay? And less nice means we're just going to be more clever about how we use our table to fill out the information, okay? But let's put some in order next to what we're going to find here, sort of like a roadmap for ourselves, if you will. So if I see an equation in standard form, a quadratic equation in standard form, then the first thing I'm going to do is I'm going to go ahead and find the vertex, okay? And once I find the vertex, I'm going to go ahead and determine the equation for the axis of symmetry, all right? After that, I might find the y-intercept, and then I'm going to find the x-intercepts, all right? I'm going to use those 4 pieces of information to fill out the table with nice whole numbers, okay? So I'm going to choose things that give me whole numbers and not too many decimal. Once we do this, we'll go ahead and graph what we have. We'll finish off with our domain and then our range, and our range should be pretty easy to see from our picture. Okay, so I know this is sort of a all-around order, but let's get started with the coordinates of our vertex. So it turns out when we have something in standard form, okay, and we've actually seen this formula before, if we plug our b and our a from the standard form equation into negative b over 2a, we will find the x-intercept of our vertex, or sorry, the x-coordinate of our vertex. So zooming back up, my b is 5 and my a is 2. And that might even be worth writing out here before you get too far. A is 3, b is 5, and c is negative 2. Okay, just so we have those numbers. So our b is 5, so negative 5 over 2 times 3, okay? And we can see that this is negative 5/6. We got a fraction here, kind of gross. Now, some fractions, I would say, like if it's a half or a quarter, I really want us to be able to work with those. But since we have a 5/6, I'd say this would be an example of one that either I would make the numbers nicer, or I would say we could have a calculator on this one, okay? So to find the y, we're just going to plug our x coordinate back into our equation, 3x squared plus 5x minus 2. So 3x squared plus 5x minus 2, and that will give us our y value, okay? So let me just go ahead and plug those into the calculator. Let's see what we get. And I believe we get negative 0.83-ish and negative 4.083. Okay. So if someone were to give you these numbers, and by that someone I mean me, these would be ones that I'd say, all right, this is like a calculator worthy question, right? Either way, we want to write our coordinate as our x, comma, our y coordinate. And let's actually just be all decimals here, negative 0.83, comma, negative 4.083, okay? So this, to me, is, I found the vertex, but it's not a nice number, so I'm not going to put it on the graph yet, okay? But as ugly as these numbers are, I can still determine the equation for the axis of symmetry, because it's always going to be x equals whatever the x coordinate of the vertex is, okay? So even though the number is ugly, it doesn't change the concept here. All right, so we found the vertex and the equation for the axis of symmetry. Let's go ahead and find the y-intercept. And our y-intercept is when we put in x equals 0, right? Everywhere we see x. So y equals 3 times 0 squared plus 5 times 0 minus 2. So we get 0 plus 0 minus 2, which is negative 2. And this gives us a y-intercept, let's be thorough, of 0, negative 2. Now this, my friends, is a nice whole number, right? 0, negative 2. So this is something I would feel comfortable plotting on my graph, okay? So if I sneak up here real quick, I'm going to go to the y-intercept, 0, negative 2, and just remind ourselves that that is our y-intercept, okay? Now let's find the x-intercept. So as I mentioned, this one is not as hard as the factored form, but a little bit harder, or not as hard as the vertex form, but a little bit harder than the factored form. So we're going to grab our equation, and the process is still the same. 3x squared plus 5x minus 2 is equal to 0, right? Because any x-intercept is a number, comma, 0. Now, this is actually going to be using the strategy we used in the second half of our vertex form strategy, where we set our x, we put our a times c in the top, so 3 times negative 2 is negative 6, and we took our b value and we put that on the bottom, okay? And then we want to think of numbers that multiply to make negative 6, but add to make 5, all right? And so if I have 6 and a negative 1, 6 minus 1 is 5, but 6 times negative 1 is negative 6. And what that means is instead of writing plus 5x, I can actually write plus 6x minus 1x. I can unsimplify that, okay? So let's see what we get there. 3x squared plus 6x minus 1x minus 2 equals 0, okay? And so again, I've taken this 5x and split it into these two terms. Now I'm going to factor by grouping, all right? And so what that means is we're going to grab the first two terms, find a greatest common factor, and we're going to grab the second two terms and find a greatest common factor. And so in the first two, we can pull out a 3x, so 3x, and what's left, x plus 2, minus, I'm actually going to factor out a negative 1, okay? So minus 1, I have a positive x plus a 2 equals 0. Now, again, one of the nice things about having the factoring by grouping is if this is the same as this, we know we did it right, okay? But if this is not the same as this, then we made a mistake. So it's nice that we can catch ourselves early on. Now this factors into x plus 2, that's in both terms, times what's left, 3x minus 1. And because I have these product equals 0, I can now set each of the factors equal to 0, just like the factored form. This will give me x plus 2 equals 0, or x equals negative 2. And this will give me 3x minus 1 equals 0, and x equals 1/3. Right? But now, to be thorough, we want to write these as coordinates. So negative 2 comma 0 and 1/3 comma 0. And so these x-intercepts, we can go ahead and plot on the graph, okay? Now I'm going to plot this one, and I'm going to estimate the 1/3. Like, I feel comfortable estimating 1/3. I feel less confident estimating negative 8.33. Okay, that's the only reason I'm plotting that 1/3. So if we go back up to our graph, we've got negative 2 comma 0 and a 1/3 somewhere over there. Okay, and these two are our x-intercepts. All right, now ordinarily I said let's put the vertex right in the middle, right? And then we can count out on both sides and use symmetry. But the weird thing about this uncomfortable decimal situation is that the whole numbers on either side don't really give equal distance. So what I mean by that is 0 and negative 1 are not the same distance from negative 8.3, okay? So what I'm going to do instead is I'm going to say, let's put in some whole number values based off of what we have down here and use those as a way to make sure we're plotting the right points, okay? So it's not the vertex, but I'm going to put 0 comma negative 2 in that middle spot, okay? Only because it seems like it's close enough to the middle that if I plug in points on either side, I will get the parabola, okay? So let's see what happens when we plug in 1 and negative 1, okay? Now again, because this is not the vertex, whatever I get for 1 is not going to be the same as what I get for negative 1, okay? So if I plug 1 into here, I get 3 plus 5, which is 8, minus 2, which is 6. And so I can actually plot the point 1, comma 1, 2, 3, 4, 5, 6. Okay. Now if I plug in negative 1, I get 3 minus 5 minus 2, which is negative 4. And so I can plot that point, negative 1, negative 4. Okay. Let's plot maybe one more point here, okay? And I'm going to suggest that we try negative 2. Let's see what we get when we have negative 2, okay? So if I put negative 2 into my equation, I am going to end up with, oh, sorry, we already have negative 2 at 0. That was one of our x-intercepts. Let's try plugging in negative 3 and see what we get, all right? Negative 3, if we plug it in, we get 3 times 3 times 3, which is 27, minus 15, minus 2, and that gives us 10. So I could plot that all the way up here, okay? And so even though this is not as nice and balanced as the other ones, I can see that I actually have a very skinny parabola here, okay? And so even though for the other ones, the numbers worked out really nicely, and this one, the numbers are a little grosser, the process is still the same. We just have to be open to being more flexible with the points, okay? All right, let's finish off with our domain and range. Domain, negative infinity to infinity. That's true for all quadratic functions. And the range, I start at the vertex. Where's that vertex? Negative 8.3 is the x, but I'm looking at the range, which means I want to see the y value. So my lowest point is negative 4.083, and I go all the way to infinity, right? So visually, I start here, and I keep going all the way up. All right, let's take a look at this all on one screen here. So we've got a little bit messier with the numbers, but the concept there is very similar to the other ones that we've done, okay? All right, let's do one more example. If you'd like to try example 6 on your own, please go ahead and do so. You can pause the video here. This is a great time to do that. And if you'd like to follow along for one more, we're going to do number 6 together, okay? All right, I've got an equation in factored form. Let's go ahead and list out our A, our B, and our C. All right, so A, B, and C, we've got those listed out. We're ready to be flexible in case the numbers are not as nice as the previous examples we've seen in the other videos, all right? But I think we're going to follow the same sort of strategy. We're going to find the coordinates for the vertex. Then we're going to grab that x value and make the equation for the axis of symmetry. We're going to determine the x-intercept or the y-intercept and then the x-intercepts. All right. We'll use what we have to fill in the table, but being really thoughtful about whole numbers. And we're going to graph what we can, again, being really thoughtful about whole numbers. All right. And lastly, we're going to define our domain and our range. Okay. So really similar in the flow. All right, let's start with the coordinate of the vertex. My B is -5, my A is 2. So x equals negative B over 2A, which is -5 over 2 times 2, which gives me 5/4 or 1.25, okay? So I have a decimal here, and that's okay. All right, this one's a little bit nicer than the previous one. But to find the y value, I go ahead and I plug it into the equation. 2x squared minus 5x minus 3. And when I put that all into the calculator, I should get -6.125. That means my coordinate is 1.25, comma, -6.125. A little bit nicer than last time, okay? A little bit nicer. Now, even though we have a decimal, we can say that the equation for the axis of symmetry is x equals the x value of the vertex, 1.25. All right, y-intercept. How do we find that again? We plug in 0 for x, we get a number out for y. So y equals 2, 0 squared, minus 5 times 0, and then minus 3. We crank through the numbers, we get -3, but that's not our intercept. Our intercept is 0, comma, -3, okay? And this is one nice whole number that I feel comfortable graphing on my grid, 0, comma, -3. I'm going to go ahead and pop that right on here, 0, comma, -3. Boop. That is my x-intercept. All right. Let's determine the x-intercept now. All right. The x-intercept, we have to take our function and set it equal to 0 because our x-intercept is a number, comma, 0, right? The y value is always 0. All right, let's set up to factor. Let's see, we take a times c, and we put that in the top, so 2 times -3. We take our b value, We put that on the bottom. Now I'm looking for numbers that multiply to make -6, but add to make -5. And so I end up with -6 and a +1, right? And that means instead of writing 2x squared minus 5x minus 3, I write 2x squared minus 6x plus 1x minus 3 equals 0, right? So I'm replacing this -5x with two unsimplified terms. The reason I'm doing that is so then I can, clump the first two and then the second two and find the greatest common factor for each one. The greatest common factor in the first two is 2x, and I'm left with x minus 3, plus the greatest common factor in the second one is actually just 1. 1 times x minus 3 equals 0. I'm so glad that x minus 3 and x minus 3 are both the same here. That means that I did the factoring correctly. And now I can take that x minus 3, pull it out to the front, and I'm left with 2x plus 1 equals 0. Beautiful that their product is 0, because now I can set each one equal to 0. The first one gives me x equals 3. The second one gives me -1/2. Those are not x-intercepts, though. I need to write them as a coordinate. 3, 0, and -1/2, 0. X-intercept, both seem very graphable. So I'm going to go ahead and put those on the graph. 3, 0, and -1/2, 0, x-intercepts. All right, now let's be clever about what we choose to put into our table. I think that this y-intercept seems pretty close to the center, right? Because my parabola should go something like this. Since it's close-ish to the center, let's put that 0, -3 in for our sort of like middle point on our table, okay? And then let's choose some values around that. So I'm going to try -1 and +1. When I try +1, I get 2 minus 3 minus 5. That gives me -6. So I can actually plot the point 1, -6. And when I plug in -1, I end up with 2 plus 5 minus 3, which actually gives us 4. So the point -1, 4 is also on my graph. Now, I seem to have a really good this side of my parabola, but what I'd really like is to get a good second side of the parabola. So I'm going to choose 2 more points after the 1, okay? I'm going to plug in 2. When I plug 2 in, I get -5. So here, all right? And when I plug in 3, I get 0, right? That's my x-intercept. All right. I think that's enough points for us right now. So let's go ahead and sketch these, knowing that the vertex is somewhere just down here. They're tiny little x's, okay? So I'm going to sketch this part. I'm going to go past this point to the vertex and then turn and come on back up. All right, we've got our graph. Last but not least, domain. And our range is from, let's see, I don't want 1.25. That's the x value. Range is the y value. I want -6.125. And I keep going all the way to infinity because my parabola is facing up. All right. So let's zoom in, make sure we got this all on one page for you. And that is all we have for this part 4. Come on back for a very short part 5, where we're going to look at some applications of parabola.